So now let's get into how exactly a device driver could be written in the context of the Linux OS. Okay. So I'm going to quickly talk about the device model used by Linux, right? Devices, which usually physical, they could also be some kind of virtual devices. For example, there is something called a virtual frame buffer, which is used to emulate the behavior of a virtual screen. You could have virtual terminals and, to emulate various kinds of consoles that are connected and so on. They are attached to buses, right? Of course, we have talked about so far is the AXI bus, but in practice, and that would be the platform bus. But in practice, there are other buses. You might, for example, have a PCI bus. And PCI is essentially what's called the peripheral component interface. You might, especially if you have a desktop computer, you would know that there are PCI slots into which, for example, you can plug in graphics processing units and so on. It is meant as a high speed and a high throughput bus interface. Now, the thing is, technically, all things on PCI, or for that matter, things that are connected through the I2C interface, all ultimately come and connect to the AXI or some related kind of bus that is provided inside the system. x86 processors, for example, do not use AXI. They have their own bus protocol, right? But ultimately, all of these things get mapped into whatever bus protocol the processor and motherboard and the surrounding circuitry follow. But I2C devices have their own addresses, PCI devices have their own addresses, and hence the sort of think of it as, this can be thought of as a separate bus on its own. Ultimately, all of these things need to get mapped into certain memory locations so that they can get access. What a driver does is it tries to abstract as much as possible of the device and provide some kind of a common interface that user space programs can use to talk to the device. Right? And typically what happens is that from the point of view of the operating system, they have certain things, for example, what are called character devices, which you might have seen under the directory called /dev, right? These are files which you can open, you can read from them, you can write to them, or you can run the IO control function on them. We'll get to this later, but open, read, write are just treating them as regular files. There are other attributes which fall under what is called the /sys hierarchy. Once again, we'll see examples of this later. And you might also have certain kinds of debug file systems, right? Things that are meant primarily when you're debugging the entire kernel. Not supposed to be used when you're actually running it, let's say, on a production laptop or a server. Okay? So what this means is there are different ways by which the files might be visible to the user. That is what I mean by user-facing surfaces. So how exactly does an interface to a peripheral, right? How does the mapping happen? There are MMIO registers in the hardware. The smart timer, right, in order to connect to the AXI late, had a set of registers with its own address, offsets, and so on. The driver, which is a piece of software that is contained within the kernel, right? It maps those registers by means of the IO remap function, which we talked briefly about, right? It sort of takes it from the physical location into the kernel virtual address space. And the driver also implements what's called policy. What I mean by policy is, when is another program or another function allowed to make use of, or rather is allowed to call the driver to request certain functions from the driver, send data into the driver and thereby to the device, get data from the device through the driver, and so on. All of that is policy, which gets implemented at the driver level. And the driver basically then exposes a programming interface to the users, right? And as I said, that could be, for example, a character device, a set of files under the /sys file system, or certain other kinds of user space API headers, and so on. Okay. So what we are going to do is I'll be showing you an example of how we can write a small module, right, which in turn can be loaded into the Linux kernel, and we'll be using the same sort of hardware idea that we had from previous weeks, right? We'll have a smart timer, which has a control register registers for period and duty, and something where I can check the status. And as we'll see, what the view that I would like to present to the users is, once this hardware has been connected to my system and I load my driver, whatever it is that I'm going to write, suddenly, magically at that point, there will be a new file which is created in my operating system, which is called /dev/vreg demo. And there will be a few other files which come under this directory called /sys, right? By reading those things, I will be able, for example, or reading or writing, I'll be able to change the value of period, duty cycle, or check the value of the status, and so on, right? So all of these things will be seen as part of an exec code demonstration. But in order to understand that, the typical sort of flow is what I want to talk about briefly over here, right? As I said, the kernel, rather than directly trying to dereference a pointer, right, goes through the virtual address. I declare a pointer as an IOMEM type pointer, and I use essentially a kind of a remap function, right? So this devm IO remap resource is a kernel function. It's provided as part of the Linux kernel, which essentially does a kind of remap of essentially translation from physical address to kernel virtual address for a particular resource, right? And from there onwards, I can use functions like readl and writeL instead of directly sort of trying to do a star base, right? And the reason for that is because when you do accesses to memory, right, directly using the star base can get compiled in a certain way, whereas using the functions readl and writeL add some extra functionality out there to ensure that even if you were not, for example, accessing all 32 bits or 64 bits, let's say you're accessing a set of sub bytes, things like the other, whatever is required in order to actually handle the appropriate ordering of data or the width of data that needs to be written or read, there will be a few extra checks that are handled by these functions, right? At the end of the day, it is going to be sort of just star base equal to, or rather read from star base or write into star base and so on, right? But this does a little bit extra checks before those are that access is completed. Okay, so there are also a large number of different types of devices, right, that we end up that can be used in a typical Linux-based system. I'm just going to talk at a very high level about some of the types of systems that are there, right? We have, for example, what are called character devices. Now, when you are used a Linux system, you might have, for example, come across TTY-S0. This would typically be what happens when, let's say, you have plugged in a USB serial port or, let's say, some kind of a serial port connection. Now, what does this mean? This is essentially something that's called a character device. So a serial port is an example of a character device. Why? Because I typically read it 1 byte at a time. It is sequential IO. Similarly, an I2C peripheral would also be something like that. The input peripherals, keyboard, mouse, and so on, touch screen, all of those would also be treated as these kind of byte-oriented sequential IO devices. So those are what are typically classified as character devices, right? On the other hand, there are certain kinds of devices where I'm not specifically interested in reading 1 byte at a time. The most common example would be disk, right, where I'm usually looking at like whole pages of data, right, either like 1 kilobyte or like 4 kilobytes or some fairly large chunk of data every time I'm trying to read from it. An SD card, right, the memory card which is can be plugged into phones, laptops, and so on. The NVMe disks that would be quite popular in many systems nowadays, right? The high-speed PCI-based disk interfaces. All of these ultimately have some kind of disk-like interfaces, right? They have like the amount of data is large, and I'm typically not reading it like 1 byte at a time. I want to read pages of data at a time, which also means that that data that I read would typically be buffered, right, for higher throughput. And this is done by using something called a page cache. It's basically a cache memory to sort of improve the throughput that we get. In other words, block devices are typically things where you want high throughput, large amounts of data being transferred. There are also other kinds of things like network interfaces, pseudo devices, and so on, right? Which could also be, which are commonly found in different kinds of operating system interfaces. Now, a word about this function call that I talked about called IO control, right? So I had already mentioned that this system called open is something that you are probably familiar with in the context of reading from files. Now in C, usually what we do is we use a function called fopen, which is actually a slightly higher level of this function called open. Open is the most basic system call, right? What open does is when I call this function open, the operating system is directly invoked. The operating system then goes and checks, do I have permission to open that file? And if so, it opens it and it doesn't give me a file pointer. It gives me something called a file descriptor, which is just an integer, right? And that file descriptor is actually sufficient. I mean, I don't need to use the file pointers and thereon. This file descriptor is enough for me to go in and convey to the operating system that I want to communicate with that file. I could read from it, I could write to it, and so on. Now, reading and writing are common operations that we do with files. But as I mentioned over here, what we are actually trying to do is take something like a timer and make it look like a set of files, right? And this is not really the typical behavior of what a timer is supposed to do, right? So for example, let's say that I want to just reset the timer. I can create a virtual file where I write one into that particular file and it will get translated into something that goes and resets the timer. But what I'm actually trying to do is to send a customized control command to this timer. This function IO control is used for that. It, on top of read and write, as far as files are concerned, IO control allows me to send certain kinds of very specific functionality. What it will do is when I call this IO control, it will take this mydev reset, which is probably some hash defined number, and send that number not directly to the device, but to the driver. The driver now basically sees that an IO control was called. It sees the nature of IO control and it decides what needs to be done, right? So this essentially is used to provide certain extra functionality. IO controls can also be used on files, right? But primarily they're used more to interact with devices. Now, a word about character devices, right? Because we'll be implementing an example corresponding to a character device. They're good for small, slow amounts of data, right? For example, a mouse which is moving around and sending its inputs back to the system, right? What we need to do is that the operating system needs to be told that, yes, there is a new device. And what we will do is that we will call this function miscellaneous register to ultimately register the device with the operating system, right? Now, this sort of brings me to one part of the way that an operating system can be modified, right? Normally, what happens is the operating system is something which you are not supposed to mess around with, because if you make any changes to the operating system, if you are lucky, you will only crash your computer and you can restart. If you are unlucky, you can actually end up damaging things, right? So normally, you should not be messing around directly with an operating system. On the other hand, we want to learn how the operating system can be modified in order to include new drivers. I don't want to go into recompiling the entire operating system each time around, right? So if I can avoid it, I would like to create just maybe one small piece of software and see if I can just load that software and say, okay, this is now part of the operating system. The interesting thing is the Linux module system allows us to do exactly that, right? So in Linux, there is a concept of kernel modules. A kernel module is like an executable program, but it does not have a main function, right? Instead of that, it has a set of other predefined functions, which I can compile into some kind of a .o, an object file. Except that because it's a kernel level module, it's called a .ko file, which we will see in a moment, right? So that kernel module is compiled. It can then be loaded into memory, and then the operating system says, okay, now I know something new. I know how to talk to this particular kind of device, right? And essentially, one of the first things that that code does is that it registers the type of device with the kernel and then allows the kernel to talk to it by means of various other kinds of file-based operating systems like read, write, and so on. Okay. So, of course, this will make more sense when we look at the code. So, we'll get to that in a moment. Before doing that, we'll just take a quick look at some more background. There are two file systems, sets of files that you will find in any Linux-based environment. I'm repeatedly saying Linux. A lot of this applies to other Unix-like operating systems also. At least the /dev is very common. /sys is something a bit more Linux specific. It may not be there in all Unix-based systems. But the most common Unix-based system nowadays is Linux. So I'm sort of just going to use the word Linux when I'm talking about most of these things. So /dev is what's called a virtual file system, right? Temporary file system, right? And what it does is that it allows us to create certain kinds of special files, which, like I said, do not actually have bytes that are stored somewhere on disk. They are only virtual. They are there in the memory of the system, right? There is also a concept of what are called major number and minor number, which for the time being we'll just ignore. Those are used in order to classify the different kinds of character devices that we have. But for now, let's just ignore that part. What /dev does is that it basically provides us with a file reference which can be used for as an entry point. So in other words, let's say that I have a serial port. It gives me a file called ttys0 which I can open, and then I can read or write, and that would essentially end up communicating with a serial port. I could also have /dev/sba, which usually would correspond to a disk present in the system, right? And I can directly sort of write bytes into a particular location of the disk or read raw data directly from a disk by opening this like a file. You have to be extremely careful when you do something of that sort. It is entirely possible that you can destroy your system by writing something into /dev/sba, right? So please be aware of doing anything of that sort. Make sure you read carefully, understand what it is doing before you try something like that. There is also the so-called /sys file system or the sysfs, which is once again a virtual file system which provides a live view of various kernel objects, right, including devices, buses, and so on. It has in turn many other hierarchies /sys/devices /sys/bus and so on, which allows us to see a lot more about what is happening inside the operating system, right? And what it does is that it actually provides various small text files that can be used for certain kinds of status or control, right? And we will look at examples of both of these as we move forward.